into the world of math, AI, and one of the toughest exams ever, the Putnam competition. Imagine tackling problems so tricky that most participants score close to zero. What happens when we throw these problems at LLMs? Spoiler alert, even they struggle.
The Putnam competition is a prestigious and notoriously difficult mathematics exam for college students in North America. Known as the hardest math test in the world, it features 12 problems worth 10 points each, requiring deep insight and creative problem solving. Problems often cover algebra, number theory, geometry, combinatorics, and calculus, with deceptively simple statements but requiring elegant, non-standard solutions. The median score is famously near zero, and scoring above 20 places participants in the top percentile. Only a few individuals score above 90 out of 120. Famous winners include legendary mathematicians like John Milnor, John Conway, and Terry Teo, who scored a perfect 120. Renowned physicist Richard Feynman and computer scientist Peter Shor also participated. On the other hand, large language models are getting better and better at solving tough problems. They're already being used for everything from economics and drug discovery to simulating how humans behave. But here's the catch. The benchmarks we've been using to test these models might not be keeping up. Models like GPT-4 and Gemini Ultra are so advanced, they've surpassed human performance in many cases. That's impressive, but it also means we need new ways to really push these models and evaluate their true capabilities. This paper takes a step in that direction by offering a fresh approach, focusing on higher-level reasoning with a challenging dataset. The progress of large language models, like nearly perfect accuracy on math benchmarks, is exciting but creates a big problem. Our datasets might not be challenging enough. Even worse, there's data contamination. This means some benchmarks are already in the training data of these models, so they can just memorize answers instead of actually solving problems. To address this, a new dataset called Putnam-AXIOM was introduced. It includes tough math problems from a famous competition that requires advanced reasoning. It also features modified problems to avoid contamination. These variations make sure models can't cheat by recalling answers. Testing on this dataset shows it's really difficult. Accuracy drops significantly, even for top models like GPT-4 and math-specialized ones. This section introduces the Putnam-AXIOM dataset, which consists of 236 challenging math problems taken from decades of Putnam competitions. These problems span 11 university-level math topics like geometry, algebra, and calculus, ensuring a broad range of difficulty and content. Each problem keeps its original exam ID and difficulty rating, which helps categorize questions by complexity and topic. The dataset uses standardized formatting and vector-based diagrams so that language models can process math content seamlessly, including visual elements. Answers are enclosed in specific markers, making it easier to evaluate models by comparing exact matches rather than approximate guesses. This setup ensures fairness and reduces errors caused by formatting differences. To ensure fair and consistent evaluations, this section discusses how answers are standardized in the dataset. A special equivalence function is used to treat answers that are mathematically identical as the same, even if they look different, like matching 0.5 with 1/2. This avoids penalizing models for formatting inconsistencies. For complex problems with multiple steps, a small adjustment is added to simplify the solution into a single, boxed answer. This retains the original problem's complexity while streamlining evaluation. The dataset also introduces variations to test model robustness. By making small changes, like swapping variable names or altering numerical properties, these variations expose whether a model truly understands the problem or just memorized it. This part explains two types of problem variations designed to challenge models beyond memorization. First, variable changes replace problem-specific variable names while keeping the solution intact, testing how models handle slight modifications in contexts. Second, constant changes adjust numerical values within a problem, altering the final solution and requiring deeper reasoning. Together, these variations make sure models are solving problems conceptually rather than just recalling answers. The dataset includes functional variations for 52 problems, with the ability to generate infinite unique snapshots for evaluation. Next, the evaluation setup is described. Models are tested on both original and variation datasets. Using standardized methods, accuracy and confidence intervals are calculated to assess model performance, ensuring robust results. This section dives into the evaluation of accuracy for models using the Putnam-AXIOM dataset and its variations. A key observation is the significant drop in accuracy when models move from the original dataset to the variation dataset, as seen in the figure. This graph compares the performance of various models, showing accuracy on both datasets with confidence intervals. For instance, models like GPT-4o and Claude 3.5 experience large declines in accuracy, emphasizing the difficulty introduced by variations. The variations reveal weaknesses, especially in models that may have benefited from memorizing original questions due to data contamination. The confidence intervals also highlight that these declines are statistically significant, suggesting that the variations successfully expose gaps in reasoning ability. This provides a clearer picture of true model performance. This section dives into the performance results of various models on the Putnam-AXIOM dataset. The table provides a detailed breakdown of accuracy scores, comparing models from different categories, such as base models, instruction-tuned variants, and advanced fine-tuned models. Interestingly, even the best-performing model, labeled as O1 Preview, achieves less than half of the possible accuracy at just over 41%. Most models, including highly tuned ones like GPT-4 and Claude 3.5, fall below 20% accuracy. This highlights the dataset's significant challenge for large language models. The table also emphasizes a stark gap in performance between base models and their instruction-tuned counterparts, with tuning providing only slight improvements in most cases. These results underscore how difficult it is for models to demonstrate true mathematical reasoning on these problems. Let's dive into the error analysis of the top-performing models on the Putnam-AXIOM dataset. OpenAI's O1 Preview leads with a 41.9% accuracy, but still shows logical inconsistencies. It often follows the correct logical path, but fails in mathematical rigor. For example, the ground truth provides step-by-step proofs for every claim, while O1 Preview tends to make unsupported assumptions. This lack of justification means it misses points in evaluations that mimic human grading. Similarly, GPT-4o demonstrates logical leaps and missing rigor. For instance, it might claim certain values are minimal or maximal, but fail to prove those claims mathematically. This highlights a common shortcoming. Models can mimic reasoning steps but struggle to maintain rigorous, airtight logic throughout their solutions. Let's wrap up with some insights from the conclusion and general analysis. The authors expanded the error analysis to open-source models like Putnam Math and DeepSeek, and found a lack of rigor overshadowed by calculation errors and misunderstandings. These models often misinterpret key aspects of problems, leading to incorrect final solutions. In the conclusion, the authors emphasize that Putnam-AXIOM offers a fresh benchmark of 236 challenging mathematical problems, targeting reasoning gaps in large models. By creating variations, they generate infinite unseen problems that highlight how models degrade significantly on these altered tasks. The hope is that this dataset will push the boundaries of artificial reasoning research and create more robust evaluation methods. And that wraps up our deep dive today. Thanks for exploring this with me. If you're feeling adventurous, give a few Putnam-AXIOM problems a try yourself. After all, it's not every day we get to turn the tables on advanced models and remind them and ourselves that true mathematical insight always has room to grow.